Alrighty, now let's have a look at a couple of example problems on this. So this problem number 2 from the handout, we want to show that the midpoint of the hypotenuse of a right triangle is equidistant from all three vertices of that triangle. That is, the midpoint is the circumset of this triangle. Now, we proved this before using in constructions, but now we're going to do this with coordinate geometry here. Note that we're going to have a right triangle here, so it kind of makes sense considering the tenets we looked at the previous in the lesson. It makes sense for us to try to set it up so that we want to try to make as many things 0 as possible. Now, this is a right triangle here, so without loss of generality, we can put this in the first quadrant, make things easier for us here. So we're going to draw a sketch of this, okay? So here's my right triangle here. Let me call the right triangle PQR. Now, I'm going to put, it's pretty clear to put one of the vertices here. We're going to call this P, right? And it's pretty clear that 0, 0 works out pretty well, right? Now, in order to maximize the number of zeros we have here, what we're going to do is we're going to make it so that since these axes are already perpendicular, it makes sense for us to put the legs along the axes here. So I can basically create a triangle that looks like this. Okay, here's Q, and here's R. Now, in this situation here, we want to make sure, first off, we can't just use one variable here because we know that PQ and PR may have different lengths. So I'm going to use two variables here. I'm going to call this length A and call this length B. Now, one thing to note here, a bit of insight. We're going to be using midpoints, and midpoints require halves. So we can use A, but if we want to try to avoid fractions, one thing that we can try to do, and this is actually pretty good here, something you may want to consider, we're going to use 2A instead. So I'm going to call this 2A comma 0. By doing this, I know I'm going to create a midpoint here, and by putting a 2A here, I can avoid fractions. Similarly, over here with R, right, we know the x-coordinate is 0, and I'm going to call this 2B. Okay? So now we know that the midpoint here, let me go ahead and sketch the midpoint like this. Our midpoint here is going to be like this. I'm going to call this S, right? Now, the location of point S is just the midpoint here, so we can go ahead and set this up. It's going to be, let's see, 0 plus 2A over 2, comma, 2B plus 0 over 2. And notice that in doing this, we get 2A over 2, comma, 2B over 2, which in this case is, and you can see 2A over 2 becomes A, and 2B over 2 becomes B. So notice how this, we actually avoid using fractions here. If you just use regular A and B, you're going to get fractions, and that's not necessarily a bad thing, mind you, but it's going to be a little bit more, cumbersome. So now all we want to do is we want to show that these are all the same here. So now, because we want to show that this is equidistant from all the sides, it even says in the name equidistant, which means we're going to use the distance formula here. So now we're going to use the distance formula and show this here. So I have to calculate in this situation here. We're now going to calculate RS, PS, and QS, and I want to show they're all the same. So RS here, again, we'll go ahead and set this up. So it's going to be 0 minus A squared plus 2B minus B squared, right? So that is, in this case, negative A squared plus B squared, which is, again, the square root of A squared plus B squared. That's a good thing, okay? Now we'll do the same thing, PS here. PS is pretty easy, right? Because we see it's A minus 0 squared plus B minus 0 squared. And in this situation, again, we get A squared plus B squared, which matches what we wanted, and that looks pretty good. And now we can do QS here. QS, in this case, we do the same thing, our distance formula. It's going to be A minus 2A all squared plus B minus 0 squared, and that's going to be negative A squared plus B squared, which, as you can see here, is just A squared plus B squared. And we can see here, this is quite nice because all three of our values match, right? We can see that there's a matching here. All three of them are identical. So we can just conclude this, and we can say that since RS equals PS equals QS, S is equidistant from the vertices of the right triangle PQR, and we're done. QED. Note that in this situation here, it probably would have been better at the very beginning for me to define S as the midpoint here. So I'm going to just add a little note here. I'm going to let S be the midpoint of our Q. So we really want to make sure that we define everything here. Okay, so you can see this is our nice little setup here. Okay. Number 4. So let's look at number 4 here. So we're told that 3 consecutive sides of a rhombus have coordinates of 0, 0, A0, and BC. Prove that B squared plus C squared equals 2AB. All right. So again, we're going to sketch this out here. You'll note that the coordinates were chosen very nicely. So we have our coordinates here. That's going to be 0, 0. So let me call this rhombus. So this is P. Q is going to be over here at A0. And R is going to be at the point BC. Now, technically, we'd like to know where point S is, and as an exercise, one of the things you can do is you can try to figure out where point S is based on these variables here, but we don't really need that. We want to show that b squared plus c squared is equal to 2ab. Now, we know there's a rhombus, and one of the nice properties of the rhombus is that all the sides are congruent. So we know that we can mention that since in a rhombus, all sides are congruent, we have PQ equals QR. So now we can go ahead and set this up here. So let's go ahead and set this up. Now, the nice part about PQ is that we actually don't need to use the distance formula here because this is along a straight line. This is along the x-axis here. So the y-coordinates are not going to matter, and therefore we know the distance from P to Q is just A. Unfortunately for QR, we're going to have to use the distance formula, but that's okay. We'll use the distance formula here. So it's going to be B minus A all squared plus C minus 0 all squared. So we can use the distance formula like this, and now we know this is the case here. So we now have to somehow turn this into that. Okay, no big deal. I see a square root over here. I like to square both sides. Let's square both sides here. So we have a squared is equal to b minus a all squared plus c squared. Okay, this is looking not bad here. As you can see, we got a c squared here. We got the pieces in here. I've got this, so I guess we're going to have to use a little bit of algebra here. So let's go ahead and multiply this out. So b minus a all squared should be just b squared minus 2ab plus a squared plus c squared. And we know this is the case here. So this is looking pretty good, right? Now we know that there's an a squared on both sides, so I can subtract a squared from both sides here. We can see that those are going to cancel out. We're left with 0 equals b squared plus c squared minus 2ab. And now it makes sense here. We're going to add 2ab to both sides here. We can cancel that out, and therefore we know that 2ab equals b squared plus c squared. And that is exactly what we wanted to prove.